So good afternoon. You are welcome to the fourth week of the facilitation for PHY313 for year 2022. So far, so good. We have covered the main three topics, which are the function of complex variable, Cauchy sequence, how to solve Cauchy sequence, and how to perform some linear algebra on complex variables. So this week, we shall be going on with our plans, with our classification plans. And for the fourth week, we have in stock to discuss geometric interpretation of complex function. So where we shall be looking at how to express complex function in a polar form, then how to generate a parametric equation using the complex arithmetic and many more. So, but before I move further, I would like to ask if you have questions concerning what we have discussed so far in the last 3 weeks. If you have any challenge, you can ask me so that we look at it critically before we move to the next thing. Any question? Is there anybody in the house that wish to ask one or two questions? Okay. In the absence of no questions, so let's start this week class. For this week, we need to understand what is called the polar form of complex number. Last week and week before last week, we actually dealt with complex number using the symbols Z, X, Y, and I. So I said in a polar form, complex number are represented as the combination of the modulus R and the argument theta of the complex number. So what I'm trying to say is that the ones we have discussed so far, we can actually write complex number as Z is equal to X plus IY, which is referred to as a rectangular form. But we can as well write this in a polar form where we take into consideration the angles. So here we can write that Z is equal to R cos theta plus I R sin theta. The question now is that what is R cos theta? R cos theta is more or less like X and I sin theta is more or less like Y. If you look at this picture, this Cartesian coordinate that I draw here, you see that we have along this direction, I call it X, along this direction, I call it Y, then the hypotenuse, which is R now, which is the modulus. Then there is an angle theta here. If we say sin theta now, sin theta is opposite all over hypotenuse. You can see Y over R. If you cross multiply, you have your Y to equal to this. If you replace Y here with this, you have this. The same thing for cos. X adjacent over hypotenuse, you have this. If you replace X here with this, you have this. So we have transformed the rectangular form to the polar form. So if you look at it critically, something common to them, which is R. That's why we have R here. And this gives us cos theta plus I sin theta. The whole of this expression can also be written in the form of Euler's form, which is exponential I theta. We get to know that in the next discussion. So I try to break it down for you to be able to understand what this thing actually is. So if you try to substitute using Pythagoras theorem, you have this expression and your theta will now be tan y over this. So now, do you have any question on that? Okay, fine. In the absence of no questions, so let's go to our lecture's note. So in the lecture note, there are some few things that I need to point out to you here so that it will actually help us in the critical analysis of what we are trying to do. So, under the geometric interpretation of a complex function, we say that if D is the domain of real value function such that uxy and vxy is the equations, so we can write u to equals to this, that is u now is a function of x and y, and v also is a function of x and y. So to describe a transformation or a mapping from D, that is from one subset to another one, in D, in the xy plane into the uv plane, so also called the w plane. Therefore, we can also consider the function that f of z is equals to the combination of u of xy plus I v of xy. So to transform this from the set this to this, that is more or less like what we call mapping. So if you look at this now, we are moving from this domain to this domain. So we are mapping A here to A here and B onto this as well. So now let's look at examples, how to solve problem. Now say express f of z to equals to z to the power of 5 plus 4z to the power of 2 minus 6 in a polar form. Now we are asked to transform this equation into the polar form. So now, how do we solve this problem? We can express z to equals to r exponential high theta. So if you look at this now, where you see z now, they substituted this now, r e I exponential, because it is in polar form. So whenever you see z in this expression, you put that value. By the time you open and you expand, you collect the like time, you have an expression like this. At the end of the day, the whole of this now, which does not contain I, are classified as U, and those that has I are classified as V, but they have two variables, R and theta. That's why you have UR theta plus IVR theta. So you have technically expressed this in a polar form, writing this. So you can see that below it says so that U of R is equals to this minus this and V is equals to this. So there are other examples in this lecture note, which I will expect you to try as much as possible to look into and solve. This is another example here called example 5. It says the ellipse center at the origin with a horizontal major axis of 4 units and vertical minor axis of 2 units can be represented by the parametric equation. That is this equation of this one. Suppose we wanted to rotate the ellipse by an angle of pi over 6 radians and shift the center of the ellipse 2 units to the right and 1 unit up. So 2 units to the right, that is along the x, and 1 unit up, that's along the y. Using complex arithmetic, we can easily generate a parametric equation that does so. So if you look at this expression now, we have x to equals to this. Now they are not writing it as x of t exponential this, because this is more or less like your theta given in this expression. So plus 2I. So by the time you expand this expression now, by the time you expand these expressions, you break it down, you have a solution. Look at the analysis now. The polar form of the original ellipse, this is the ellipse now. You have s of t to equals to 2 plus this. Now, when it moves, r of t now, it moves s of t exponential I pi theta. So also 2 plus I. So another example is example 6 that show that the image of the right. So this is not so clear, but we can actually look at it from another perspective. So there is one example here which I would like us to look at it together and try to figure out one or two things and understand one or two things there. So if you look at this uh, problem, we are given this expression that z is equals to this, 4 this plus this. So what you are expected to do here is to rewrite this expression in a geometrical form. So in that case, you collect all the one that has I to one side and the one without I to the other side. So you have all this one here, which can now be written as u as a function of x and y, and the whole of this one, which is b, as a function of x and y. So now let's look at this expansion. Let's say expect the function f of z to equals to z bar real of z plus z square plus imaginary of z in the form of f of z in the form this. So that if we should rewrite this in this form. So what we're expected to do here is that, z, in this case, they are not asking us to take it to a polar form. So it's just ordinary z. So we know that z can be written as z is equal to x plus iy. So where you see z, you put z, x is equals to, z is equals to x plus iy. Now, the inverse of z, I've discussed this 3 weeks ago, is more or less that changing the sign, the operational sign in between x and y. So initially it is plus, but by the time you have the bar, it will be negative. That is why you see this one here is replaced with x minus iy. Then the real of z is x, then plus z itself, which is this square, then the imaginary of z is y. So expanding it, you have something like this. Then you can now write that the whole of this is us of y and the whole of this is vs of y. So example 1 and 2 show how to find us of y and vs of y when a rule for computing f is given. Consequently, if us of y and vs of y are two real value function of the real variable s and y, they determine a complex value function, which is this now. F of z is equals to this. This is a complex value function. We can use this formula. Now, how do you determine what is x and what is y? So if you have something like this, you can substitute your x with z plus z bar over 2 and y with z minus z bar over 2i to find a formula for f involving the variable z and z bar. An example is this. Say example 3, express f of z is equals to 4x squared plus I 4y squared by a formula involving the variable z and x bar. So what we are trying to do here is we are trying to find a way to transform this function f of z is equals to this to a function that has z and z bar as its variable. So if you look at x now, we can actually replace x with this. So that is why you have x, the whole of this squared, then y you can replace it with negative of this, which is this. So by the time you square this and you expand and perform algebra on it, you eventually get this, and you collect the like times and break it down further, you have your result. So this is how to move from x to z or z bar when you are given an f of x as a function of x and f of z as a function of x and y. So you can go in between x and y, provided you remember this relationship between x and z bar. Any questions? Any questions? Questions? Okay, in the absence of question, now what we have just tried to look at today is to see how geometric complex variable is or complex functions are. So we have solved some of the problem and we have seen how to transform from x to z. So in summary, we said that if d is the domain of real value function of this and v is this, the equation of this is this. Describe a transformation of or mapping from d in the xy plane into uv plane, also called the w plane. Therefore, we can also consider the function this. This we have discussed. So for you to master the technique very well, I will advise you to try as much as possible to try to solve all these problems. The first one there is that you have to express f of z to equal to by a formula involving variable z. That is, you should transform this to z and z bar. And also, we have to write this in a polar form. We know that once we have z, z is equal to r exponential I theta. So where you see z, you put that value, then you expand. So we have to rewrite this in the form of this. That we know your z, you put the value there, then you expand it. Z is equal to x plus iy. So to the power of 4, expand it and collect the one with I and those without I, then you can write it in this form. So we also have to prove that cos z, sin z, cos z, and sin z are entire function. All this you can find the proof on the internet. Just go to Google and type cos z or sin z cos z. You see the proving. So just look at all this and try to solve some of the problems so that you can master the techniques. So the last one is what is the idea that led to the Cauchy-Riemann equations? So this we discussed last week. If you go back to the note and try to understand the procedures in the note, you will see the reason why we need to look at Cauchy-Riemann equations. So lastly, any questions? Any questions? Okay. In the absence of no questions, uh, we are going to stop the class today. So next week, we continue with analytic functions. So that's the next thing we are going to discuss from next week, analytic function. So please take your time to go through the lecture notes and read one or two things so that in the next class, we can actually interact and ask questions on areas that are not so clear to us. So once again, thank you for coming. So see you next week.